ABC Calc students, this is your day 34 notes. Today we're going to talk about more related relates, and we're going to talk about related relates in questions where we have the angles changing. So that's going to be a little bit different for us. So we've done 2 days of related rates up until this point, and now we're going to see how if we have today specifically a triangle where an angle is increasing at a given rate, how does that affect some of the side lengths of that triangle? So a little bit different, but stuff that we've seen in the past. Some good pre-calc stuff is going to come in today to help us with that question. So we do have a quiz tomorrow. Well, the quiz tomorrow will cover some things like mean value theorem, quadratic approximation and error that came up on the last quiz, curve sketching from the last quiz, max min, just general differentiation, and related rates. Now, we've only really started recently talking about related rates. So, as far as what we would think about related rates coming up on this quiz, it's going to be something that's maybe not of the most challenging level of difficulty quite yet, but I'll give you more info about this once we get a little bit closer to the actual quiz day. So we are going to, in class tomorrow, complete number 6 from worksheet A. So I hope that you've gotten a decent way through worksheet A with related rates practice at this point. This one's about a ship leaving a port going west and then another ship leaving the same port going south. They're leaving at different times, which is kind of a big deal. So we have to make sure we pay attention to that. And we want to know how fast they're separating at noon. So if you want to start setting this up and at least thinking about the components that we need to know in order to do number 6, of course, I'll encourage you to do that, but this is not a try it question. This is something that I will officially do with you in class. So if you're looking at it for the first time with me, that would be okay. So if you go to the next page, here's our first example of dealing with related rates and angles. And the question says 2 sides of a triangle measure 15 feet and 20 feet. How fast is the third side increasing when the angle between the 2 given sides is 60 degrees and is increasing at a rate of 2 degrees per second? So we have a triangle here. We have sides that are 15 feet and 20 feet. We're given some information about the angle between those 2 sides, so I'll just label that as theta for now. I don't want to exactly fill in theta 60 quite yet because that's the when, right? We want to figure out when the angle 60, and this is the rate at which it's changing. We want to figure out how fast is this last side changing. So when we think about this last side and we think about being able to determine its length, what I'll tell you is that we can't, first of all, assume that this is any sort of right triangle. So if you think about some good old trigonometry skills where we have 2 sides and the angle in between those 2 sides, the way that we're going to approach this example is by using the law of cosines. Blast from the past, okay? So if you have side angle side in a triangle and it's a non-right triangle, side angle side is a setup for law of cosines. And law of cosines, if I label this side as C, would say that c squared equals a squared plus b squared minus 2ab cosine of angle C, okay, where angle C is the angle that's directly across from the side that I've denoted as little c. So this is going to be the formula that we use to eventually figure out how fast side C is changing given this angle. That's the when, and at that specific rate that the angle is increasing by. So let's kind of talk about what our given, want, and when are for this example. So given, we're given in terms of these lengths, it doesn't matter which one's A and which one's B, but we'll say that A is 15 and that B is 20 for this example. And what we want is the rate at which the last side is changing. So we want dc dt. And we want that when, specifically, theta is 60 degrees and d theta dt is changing at 2 degrees per second. Okay. Now, one thing we should really just establish right off the start is when we start finding the derivative of some of these pieces here, we know that when we're finding the derivative with trig functions that we really have to be thinking in sense of radians. We got burned a little bit, I think, with the differentials example. Remember back to sine of 59 degrees? If you let your change there in dx be 1 degree instead of pi over 180 radians, you got a very different result. Okay, so why don't we right off the bat, even though we're given these in degrees, think of that my when is pi over 3 radians. And therefore, if I convert the d theta dt by multiplying by pi over 180, this becomes a rate of pi over 90 radians per second. So those are going to be definitely two values that we want to use, especially when we go to do some evaluating later on. Okay. So when I go to start plugging things in here, we can already sub in our values of a and b, right? Because those are fixed values no matter what. So we have to be a little bit careful about subbing in the when part. We can't do that yet. But the given values of a and b, since those lengths are fixed, they're not changing, we can go ahead and at this point plug in 15 squared and 20 squared. We can plug in the 15 and 20 there. So to start setting the stage here, we're going to write that c squared equals 15 squared plus 20 squared minus 2 times 15 times 20. And at the end, cosine of theta. Okay. So once I have this, now I can actually find the derivative here. And I notice I'm not even cleaning this up quite yet, because when I go to find the derivative in the next step, it would be 2c times dc dt, the rate at which this last third side is changing. And the nice thing about having these constants here is that these drop out and become zeros, right, when you find the derivative. But we still have the coefficient out front here, 2 times 15 times 20. This is a total of negative 600 cos theta. So since the derivative of cosine is negative sine, this is going to become 600 sine theta times, don't forget, derivative of the inside chain rule would be my d theta dt, which of course we know that information, so we're going to be able to sub that in. So if I want, I can actually even clean this up already by saying that dc dt, if I divide the 2c over to this other side, would be 600 sine theta over 2c. So the 2 would go into that 600 3 times, 300 sine theta over c times my d theta dt. And now we can start subbing in, right? So we know that we're looking at this when theta is pi over 3. And we know d theta dt is pi over 90, but I'm really specifically not plugging in c yet because we don't know c, do we? Oops. Oh, so c is one of those hidden unknowns. Okay. So how am I going to find the value of c? Well, we're going to find the value of c by using law of cosines when the angle is 60 degrees or pi over 3. So to find the value of c, which would equal technically the square root of all this, right? Let me see how small I can write this in here. So c is going to be the square root of, let's see if I can have tiny handwriting, 15 squared plus 20 squared minus 2 times 15 times 20. And then at the end, cosine of, we're finding this when the angle theta is pi over 3. Just squeezed it in there. Okay. So when you do this, the nice thing about pi over 3 is our angle is, it's a special angle for sine and cos evaluating. In fact, cosine of pi over 3 is a half. So if you were to simplify this by figuring out what this number is underneath the radical, the simplified version here is going to wind up being 5 radical 13. Okay. So once you have that all simplified, and if you don't believe me, again, double check that whatever that number is, it would be 25 times 13. Okay. So now that I have that value of c, come on back down here, plug it in. So we had that hidden unknown we had to deal with there. And in terms of simplifying from here, we're going to leave this in radical form. So certainly don't type this into the calculator. We want to leave pi in our final answer. Sine of pi over 3 is not 1/2 like cos pi over 3 is. It's radical 3 over 2 if we use special triangles. So we get 300 times radical 3 over 2 over 5 radical 13 times pi over 90. And you can start cleaning a lot of this up here. I don't know how much cross canceling can I do here. 2 goes into the 300. That would be 150 that I'm left with. Oh, and then 5 goes into that 30 times. Oh, and then 30 goes into 90 over here 3 times. So when all is said and done from doing that simplifying, it looks like we get pi radical 3 in the numerator. And in the denominator, we get 3 times the radical 13. Okay. And just because it seems like the answers, it's not always the case for AP questions. but sometimes they will rationalize and try and clean this up a little bit. So if you multiply the top and bottom by radical 13, we're going to get that the rate at which side C is changing is pi radical 39 in the numerator over 3 times 13, which is 39. And that's changing at a rate of feet per second. Okay, pi radical 39 over 39 feet per second. Now, again, we would not have gotten the right answer if I didn't use the d theta dt in radians. You know, sine 60, sine pi over 3, of course, those have the same value here, but it's really all about that d theta dt really must be in radians. So please make sure you're making those conversions where appropriate. And just as a quick reference here, like what is pi radical 39 over 39? It's approximately changing at half of a foot per second. Okay, just as kind of a quick reference point there. All right, so when all said and done, you know, it's a lot of algebra that hopefully you're familiar with. I mean, this is definitely from pre-calc, law of cosines. You know, maybe we wouldn't have jumped to that right away as an initial thought, but especially if you don't have a right triangle, you got to default to law of cosines. And when we sub in, of course, we're going to run in situations where we get these hidden unknowns that all of a sudden we have to find. And don't forget about radians, radians, radians. Okay. All right. So I really like that one. This last one is a question from good old 1984. Such a great year. Maybe I've told you why 1984 was a great year before, but I'll let you make a guess as to why it was a great year. So what do we have? A ladder leaning against a building. Oh boy. This is the third day in a row where we have ladders leaning against buildings. I guess we do that a lot. Okay, so that end X is on level ground and end Y is on the wall. X is moved away from the building at a constant rate of half of a foot per second. So it's even the same scenario, isn't it, right? The base of the ladder is moving out from the wall at a rate of half a foot per second. Find the rate in feet per second at which the length OY, okay, so OY is going to wind up being the vertical component here, is changing when X is 9 feet from the building. So just to make sure that we have it labeled correctly, and I'm going to make you do this question on your own. Let's do it traditionally, how I think we would set it up based on similar examples we've done in the past 2 lessons. But then I'm also going to show you how we can model the same thing parametrically, so that if this were a question on a calculator section of the AP, we could actually approach it from that perspective as well. Okay. So when they're talking about the end X being on level ground and the end Y being against the wall, and then we have this point O right here, which we would kind of think of as being the origin. We know that in this case that the ladder has a length of 15 feet. And we know that the rate of change dx dt is 0.5. And when it's moving out from the wall, we therefore know that this is decreasing at a specific rate. So in the end, we are going to want to find dy dt. It's the same setup though, guys, right? As the last 2 lessons that we've seen these ladder questions in. So I'm going to encourage you at this point, hit pause, because I'm going to show you the answer. But please make sure you hit pause, try to figure out what the rate of change is that the top of the ladder is moving down the wall with. And then also find the rate of change in square feet per second of the area of triangle XOY, which we did that question the other day for the first time as well. Is the area increasing? Is the area decreasing when X is 9 feet specifically from the building? Okay, so that's the when part. Go ahead and set yourself up there. And again, if you're hitting pause, that's what I'd encourage you to do, such that you can check your answers with me in about 2 seconds here. Okay. So what I definitely need to do is cover up the right side, because I'll do that parametrically with you in a second. All right, let's see how crafty I can get here. Okay. So based on our setup here, we know Pythagorean theorem is the way to go. X squared plus y squared equals the length of the ladder is definitely not changing, 15 squared. So find the derivative. This is looking really familiar from the past few days. Derivative of a constant, don't forget, is 0. Okay, so then plug in what we know. So we have 2 times, we wanted this when X equals 9. So that was the when that was given up at the top. Dx dt was given as half a foot per second. 2 times 12 was a hidden unknown, by the way. Hopefully you figured that out pretty easily. It's also a nice Pythagorean triple. Dy dt, and then from there, once you move the 9 to the other side, what that is, and then divide by 24, it does reduce to -3/8 feet per second would be the rate at which the top of the ladder is moving down the wall. So pretty classic, very similar to the examples we've done over the past few days. So then how do we figure out the rate at which the area is changing? So area would be 1/2 base times height, which in this example would be representative of x and y. I really hope you remember to do the product rule here. So when you find dA dt, we get 1/2 derivative of the second times the first plus the derivative of the first times the second. Okay. Plug in what we know. Okay, we already found dy dt in the last step. And then cleaning all that up, you should have found that in the end, the rate at which the area is changing when x equals 9, specifically at that instant, is 21/16 feet squared per second. Okay, so I think that comes out to be like 1.3125 square feet per second. So checking in here, hopefully that made sense to you. If you made little errors in the process, I hope that my work here helps you to fix those little mistakes. But what we now need to do is kind of go over to the other side and think about how can we do this same type of question, but model it parametrically. All right, so I'm going to jump back over here and we'll set up the same exact picture, but we have to think about changing our mindset a little bit when we think about defining these things parametrically. So here's my ladder still. All right, and we're going to get two pairs of parametric equations, one to represent what's going on for the base here, and then what represents the height. And remember that we're really trying to figure out how this height is changing as time goes on. So if we represent this coordinate right here as at any given time 0.5t, 0, we're going to define this to be x1t and this to be y1 of t. Okay, so our first pair of parametrics represents kind of the rate and the path at which the base of the ladder is moving away from the wall as it's sliding out. And it's moving according to that rate of 1/2 foot per second. So hopefully that makes sense there. When I go to define this point up here, it's a little bit tougher because remember, we don't know, we know that x is 0 at this point, but how are we going to find y2 of t? Okay. So to figure out the height, what we're going to do in general with respect to time is remember that this is 15 still. So if this is x1t and this is y2t, we could define y2t, the y value here, as being from Pythagorean theorem, the square root of 15 squared minus x1t squared. Okay. So we can clean this up by making that 22 or 225 minus, now you can plug in 0.5t squared there, you can leave it as x1 of t squared, it's really up to you. It doesn't really matter, I guess, what we decide to substitute in here, because we can define on the calculator x1t to be in this location. But what we have to know is that the y2t position is going to be equal to that. Okay, and what we're trying to find is we're trying to find the rate of change of how fast this is moving down the wall here. So to find that rate of change, we're finding the derivative of this at a specific time. Well, what time are we trying to figure this out at? Remember, when x is equal to 9. How much time has passed when x equals 9? Well, if I think of the x value right here, if 0.5t is equal to 9, then hopefully we can easily get that. It takes 18 seconds, right? Half of 18 would be 9, so that makes sense. It takes 18 seconds for the x value to be 9. So we want to figure out what is the derivative, what's the rate of change of y2t when t equals 18. So let's go ahead and type these into define these in the calculator, x1, y1t, and then x2 and y2t. And then we'll see what we're going to wind up doing to calculate the derivative at time equals 18. So for x1t, we're going to type in 0.5t, and then y1 of t is 0. Okay. x2t is always going to be 0, and then y2 of t we saw is the square root of 225 minus, and again, we can easily type in x1 of t squared by doing alpha trace, and you'll notice that all of our parametric variables appear here. So x1 of t squared So excellent, we've got all that set. And you can look at this graphically if you want. So if actually, I'll show you really quick. If I hit graph, it's maybe a little tough to see here. Oh, my dog's barking. Callie, be quiet. Shh. Talking about parametrics here. Okay, it's a little tough to see, but I did define the little bubble here, so you can see the rate at which the ladder is moving away from the wall, and then you can see the ladder sliding down the wall over here. I don't know if you can really tell because they're actually pretty close to each other, but the ladder is moving away from the wall faster than it's sliding down the wall. Ooh, and at the end it goes down real fast, right? So if you think about what the answer was from the traditional way, that makes sense actually, because the rate at that time was slower, that it was moving down than it was moving away. Okay, how am I going to use all this? So quit that screen real quick. Let's do the derivative of y2 of t at time equals 18. So I don't even know if we've done this much where we've done numerical derivatives at specific times with parametrics, but here's what we're going to wind up entering in to answer part A. We're going to find the derivative with respect to time of y2 of t at time t equals 18. All right, so in order to do that on the home screen, we're going to hit Math 8 for nderive, the derivative with respect to time. Now, that same button that we used to hit X in function mode, now we'll just plug in a t for us since we're in parametric mode. We want y2 of t there, so again, alpha trace gives me my options there. Y2 of t is option 4. At time t equals 18 is, lo and behold, negative 0.375. So negative 0.375 is the negative 3/8 feet per second that we got on the traditional side, which is good news. We don't want to get a different answer if we model this parametrically. And then finally, for the area part, we can do that parametrically as well. Maybe I'll go down to a third line, x3 of t and y3 of t. So again, in terms of defining this, if you want to let x3 of t be x1 of t, this is just one approach here. We can define y3 of t if we want to find the rate of change of the area to be the area then. So it's 1/2 of x1 of t. Remember that the height is what y2 of t is. So as long as we have that inputted correctly into x3 and y3, let's come on down here. So to get x1 of t and x3, alpha trace, it's the first option. And then we're going to type in 0.5 of alpha trace x1t, and then alpha trace choice 4 for y2 of t. All right, go back to the home screen. We want to find the derivative now with respect to t of y3 of t, right, where we have our area function. Again, since we're dealing with x equals 9, that corresponds with t equals 18. We're almost there. We're in the home stretch. Math 8, ddt of y3 of t, alpha trace. We want option 6. At time t equals 18 is 1.31249999999. Okay, well that to me sounds like 1.3125. And 21/16 is 1.3125. Remember, this is feet squared per second. So if you like parametrics and you can get a good sense of this in a parametric perspective, then this is, of course, a valid way to approach this problem and get the same exact answers that we got from doing it traditionally. So you would have had, I guess, either option, especially if it's a calculator question. You can model this parametrically and get the same results. If I had a guess, and maybe I'll take a poll next time I see you in class, I'm guessing a lot of us probably are going to stick with the traditional way. But it's nice to have multiple ways of modeling the situation. So let me know if you have any questions about that next time you see me. But like I said, maybe I'll take a quick poll, see how many we like the traditional, how many like the parametrics. All right, have a great rest of your day, and we'll do that number 6 from worksheet A next time I see you.